Good evening and welcome to another Parliamentary and Scientific Committee discussion evening. One of our ongoing series of virtual meetings, which I think we've all got quite used to now. I'm delighted that this evening's discussion is on the transition to net zero, organised in cooperation with the Met Office. There is no doubt tackling the effects of climate change is a huge challenge and will go long into the future as we address how we are actually going to do that and how we are going to meet our commitment to meet net zero by 2050 and what the transition path to that looks like. I think we have made and are making progress, but of course now there is a need to both scale up and to increase the sense of urgency around how we do that and how we do reach our commitments. And that transition is going to be a huge challenge, but I think there are also huge opportunities within that, and I hope that we will discuss some of those this evening. Now, usual housekeeping rules, of course, which is please keep yourselves on mute when not making a contribution. Just helps to improve the sound quality. If you are wanting to ask a question, please could you use the Q&A function, which you will find at the bottom of your screen. The danger if we use the chat or hands up is I miss it. So if we can keep everything corralled into the Q&A, that would be very helpful indeed. Right, I think therefore we are ready to start. I have four very distinguished speakers this evening who are going to address different aspects of the transition to net zero, and I'm going to invite each of them to speak to us for up to 10 minutes. I will keep an eye on the clock, and to the speakers will give you a nudge if you're going too far over. I can be a bit lenient because we want to hear what you have to say, but we obviously do want to leave some time for questions and answers at the end as well. So on with the show, as they say. Our first speaker is Professor Jason Lowe, who is Head of Climate Services for Government at the Met Office. And Jason, I believe, is going to talk to us or give us an introduction to the current challenges posed by climate change. Jason, 10 minutes, please.
Thank you very much for the introduction. So what I want to do is firstly have a look at the evidence that the climate is changing and understand how much and how fast it's changing. Then I want to look the other way. I want to look into the future and understand just initially what some of the models that we have of the climate system are really telling us. And I want to use that as a base for a jumping off point for the talks that follow. I'm going to attempt to share my screen. Just bear with me for a moment. And unfortunately, the actual... Okay, let me try something else. Can you see that okay?
We can, thank you.
Great. So let's start with the global average temperature. On the left-hand side of the screen, what we've done is we've put several alternative data sets together, and we've looked to see how the global average near surface temperature evolves from around 1850, so around the time of the Industrial Revolution getting going, all the way up to present day. And the first thing you can see is there are lots of wiggles. Natural variability of the climate system is something we're all familiar with. We see one summer's maybe warmer than the last one, then maybe we get a cool summer, then maybe we get 2 or 3 warm summers. But variability is important. It's important in the past, and it will be important in the future. And when we talk about climate change, what we need to think about is that interaction of climate change with variability on top of it. We can see overall there's an upward trend. And if we look at the last decade, it's around 1.1 degrees above the pre-industrial level. And remember, that's a global average. Some places warm more, some maybe slightly less. And typically what we've seen is that the land warms faster than the ocean, and also some of the high northern latitudes warm at a faster rate. If we look to the right, it reminds us that other parts of the climate system are also changing. So we've seen the atmospheric carbon dioxide concentration increase from around 275 parts per million up to in excess of 400 parts per million in recent years, and that continues to rise. We also see changes in other iconic parts of the climate system. So we've seen drops in Arctic sea ice, and that downward trend we've seen throughout the satellite record period from around 1979. If we look at the Arctic minima in September, then we see a reduction of around 13% per decade. We've seen sea level rise. We can measure this throughout the global coastline. It's currently rising at around 3 centimeters per decade. Glaciers have been losing mass, but also so have the large ice sheets, Greenland and the Antarctic ice sheet. And importantly, if we measure the heat content of the ocean, we've seen significant increases. And that's really important because around 90% of the extra heat that we're trapping in the climate system because of human-driven global warming is finding its way into the ocean. So we can look across the entire system and see this consistent signal that fits our physical understanding. If we look at the UK, we're seeing changes in extreme weather. On the left is an infographic where we compared 30-year period centered on 1975 with very recent decade. And over that time, we've seen increases in the hottest day of the year, around 0.8 degrees Celsius. The coldest day of the year has become milder by around 1.7 degrees Celsius. Warm spells have increased in length. We've had fewer days where the maximum temperature never rises above 0 degrees. And important from an impacts perspective, if we look at the most extreme rainfall days, then the total rainfall falling on those days has increased by around 17%. Now, those are, if you like, the raw measurements. We also have approaches that let us look at, well, can we link the long-term change in climate to these individual extreme events, a so-called attribution problem? And we're seeing, for instance, if we look at events like the Southern England floods in 2013-14, that because of climate change, the event was more severe and more likely to occur. And we need to remember that these are expensive events, in that case, more than £1 billion worth of damage. If we look at the heat wave in 2018, that was 30 times more likely because of climate change. And again, we remember the impacts, this time's in terms of excess deaths connected with the event. Not all extreme weather events can be connected with climate change because of the large natural variability, but a significant number can in the UK and globally. If we focus now on the future, so here we take our understanding of the climate system and build this understanding into mathematical models. And we use our computers to solve those mathematical models and give us a range of views as to what the future could look like. On the left-hand panel, I'm looking at around 400 alternative views in how global emissions of carbon dioxide might change in a period out to 2100. And I mean, these depend on the things you would expect. They depend on what we assume about the increasing GDP of the world, what we assume about global population, what we assume about global trade, and what we assume about technology. And it's useful to look across a range of these scenarios. The ones I've colored in blue, they bring us to below 2 degrees of global average warming above pre-industrial levels at the end of the century. The ones in green limit us to below 1.5 degrees. You'll probably be aware that the Paris target agreed in 2015 is to stay well below 2 degrees and ideally aim to stay below 1.5 degrees in order to avoid some of the worst impacts of the changing climate. You can see that those 1.5 and 2 degree scenarios, they involve rapid reductions in greenhouse gas emissions. I'm showing carbon dioxide, but we also would need to reduce other greenhouse gases too. You can see that all of the green lines and some of the blue lines actually go below zero. So that implies the need to actively remove carbon dioxide, not just reduce the sources. And you can see in the green lines that we're reaching a net zero for carbon dioxide around the middle of the century. The right-hand plot is showing the median temperature response. And what you can see there is that there are pathways that are consistent with limiting warming to 1.5 or 2 degrees. In this case, we've looked at the probability of doing that, of being around 50% or more. You can also see these grey lines. These grey lines are showing us alternative futures where we don't reduce emissions so rapidly and we lead to higher temperatures. If we took current policies and said, well, where does that take us? On the figure on the right, it would take us to around 3 degrees of warming. Finally, you can see that even with the very strong mitigation, strong reduction in emissions, we are not able to eliminate all of the future warming. So alongside mitigation, if we want to avoid those impacts, we would also need adaptation. My final slide is looking briefly at what we can expect for the UK. And this is drawing on a data set called UK CP18 that was funded by BEIS and DEFRA and involved a team that also included the Environment Agency. And if we look on the left-hand side, we see increases in temperature are predicted, but the amount depends on the emissions of greenhouse gases, how much the globe chooses to emit. And in the lower scenario, we're seeing a temperature increase centered on around 1 degree, but with a spread that goes up to perhaps 2.5 or 3 degrees. In the high emission cases where we don't limit emissions, we're seeing central estimate of warming in excess of 4 degrees by the end of the century, and a possibility of reaching 6 or 7 degrees. The maps at the bottom show that all parts of the UK are expected to warm, but some parts more than others. We see this gradient south to north with greater warming in the south. On the right-hand side, we're looking at changes in precipitation, rainfall and snowfall. And in the summer, we expect a reduction in rainfall. So the central case suggests a reduction of about 25%. In the winter, we're expecting an increase somewhere between 20 and 30%. So the global total is partly offsetting each other. But how the UK deals with water will need to be very different. And also, if we looked at extreme rainfall, for instance, the 2-year return period event, we might expect that to increase quite significantly, perhaps by of the order of 25%. And these are connected with impacts. So what do we do about it? I'm going to stop sharing there and hand over back to Stephen and then on to the next speaker.
Jason, brilliant. Thank you. I think you laid out very clearly the challenge, or the various different challenges we face and the various options. Just a quick question from me, and hopefully some of the others will come up in the Q&A. But when we talk about a 0.8 degree increase since 1990 to 2020, do you think that the public understand that that's a relatively small number, but has a huge impact? And are we winning that messaging battle with the public that they want to take the steps needed to tackle this?
Yeah, so it's very interesting. I mean, there's a lot of literature now about this aspect of public communication. And I think when you see numbers, especially those connected with the summer, of being somewhat warmer, but numbers that people go, well, actually, that's less difference than it was yesterday when I looked at the weather forecast. what we're finding is resonating more is when we look at extreme events, those events that people see in the news or see in their neighborhood that are connected with impacts. And I think increasingly people are realizing that, even in the present day, those weather impacts cause quite significant, severe problems that are expensive, that are damaging. And the part of the story that is really explaining, well, those events are becoming more likely because of climate change, that's having real traction, I think, with members of the public.
Brilliant, thank you for that. Right, as you said, we will now move on to the next part of the story, which is with Professor Jim Skea, who is Professor of Sustainable Energy, Imperial College London, and co-chair of the IPCC Working Group 3. And Jim is going to talk to us about the future mitigation paths available to us and what these might look like. Jim, 10 minutes, please.
You're muted there, Jim.
You're quite right. My apologies for that. I've got it right all day, then blew it on the night. Right. Okay, so I'll pick up the mitigation story that Jason started. And just to say that I will be taking largely a global perspective, but I'll get onto some very specific UK kind of issues at the end. And a lot of this will be based on the IPCC special report on global warming of 1.5 degrees, which came out nearly 3 years ago now. And I'll mention at the end what's about to come from IPCC. So, my slides are not moving. There we go. Okay, so this is very similar to a slide that Jason showed. He talked about 400 different emission pathways that had been published. The blue curve on the right-hand side, the band, shows about 90 pathways that are consistent with global warming of 1.5 degrees for carbon dioxide only. And really, the key messages to take away are, to be on these pathways, we'd need to reduce global carbon dioxide emissions by about 45% by the end of this decade. And we would need to get to the fabled net zero by the middle of the 21st century. And on the right-hand side, it's showing some comparable emissions of other greenhouse gases and forcers, methane, nitrous oxide, and black carbon. They will never get to zero, but they also need to go down substantially to achieve that kind of ambition. One warning I would make is that we need to be very careful whether we're talking about net zero carbon dioxide or net zero greenhouse gases in total. So the EU and the UK have set their net zero targets in terms of total greenhouse gases. China has set it for 2060 in terms of carbon dioxide only. And basically the metric is that greenhouse gas net zero would come maybe a decade after net zero CO2. So when we have a target for 2050 for net zero greenhouse gases, it's probably about 2040 for carbon dioxide, and that distinction is really quite important. One other thing we did, the message there's more than one way of limiting warming to 1.5 degrees. And we tried to do this by picking out 4 what we called illustrative pathways for carbon dioxide emissions. And what these diagrams mean, the solid blue line is net carbon dioxide emissions. The grey area is emissions from fossil fuels and industry. The orange part is either emissions or sinks from agriculture and land use. That can be positive or negative because land can be used to take carbon dioxide out of the atmosphere. And the yellow area means bioenergy with carbon capture and storage, which is planting trees, burning the biomass, and then capturing the carbon dioxide. Quite controversial because of the land use implications. But this message is clearly showing there's a big trade-off right at the left-hand side, very, very rapid reductions in emissions from fossil fuels and industry. And as a result of that, you don't need to rely on bioenergy with carbon capture and storage towards the end of the century. But if you put off the emission reductions at the other end with pathway 4, then you need to rely a lot on carbon dioxide removal to get back to that 1.5 degrees. Just as a little bit of calibration, this pathway 1 involves emission reductions of about 7% per year for about 20 or 30 years. And as a calibration, 7% was roughly the kind of reduction in emissions we saw in 2020 because of the COVID crisis. So just to give a sense of calibration about that. Now, where are we? Well, I mean, the good news is that long-term strategies for net zero are beginning to emerge globally. So the majority of the world's emissions are now covered by net zero targets. So if we look at this graph on the right, the NZE, net zero emission pledges, about 2/3 of global emissions are now covered by these pledges for mid-century. But the problem is that there are two gaps. The Paris pledges for the short term, the so-called nationally determined contributions for 2030, do not yet set us on that pathway towards net zero, though the G7 summit that's just taken place took us in the right direction. The further gap is that policies on the ground aren't enough to allow even the current pledges to be met. But the good news is that the net zero targets have focused action and set the wheels in motion. And this graph here from the UN Environment Programme, which comes out every year, is kind of an illustration of where we are. The blue line at the top is an estimate of where current policies will take us for carbon dioxide emissions. The brown ones are the pledges that people have made, roughly getting us back to about the same level as at the moment. But this is where you would need to be for 2 degrees, well below 2 or 1.5 degrees. So the gap for even 2 degrees is about 1/4 to 1/3 of projected emissions, and the gap for the 1.5 range is about half of projected emissions. So very substantial gaps still remaining to be filled in terms of action. Now, in the report, we set out what would be needed to actually limit warming to 1.5 degrees. 3 phrases: rapid, far-reaching, and unprecedented changes. We absolutely meant each of these words. So the kind of things that were involved: a range of technologies and behavioral changes, a massive upscaling in low carbon and energy efficiency investment, factor 5. Renewables could be up to 85% of electricity supply by 2050. Steep declines in coal, essentially zero in electricity by 2050, but oil and gas, and especially gas, can persist in the system a bit longer, though by the year 2100 you would be moving towards elimination. And of course, deep emission cuts in the demand side, transport, buildings, the way that we plan to use our cities and our land. And on the right-hand side of this chart, I've taken some information from the latest International Energy Agency publication, which tried to work out what were the kind of milestones you would need to reach in order to get onto that 1.5 degrees pathway. Now, it may be a little hard to read, so let me just pick out 2 or 3 of them. By 2025, no new sales of fossil fuel boilers. By 2030, all new buildings would need to be zero carbon ready, and there would be a complete phase out of unabated coal in advanced economies. By 2040, you're looking at net zero emissions from electricity globally and a complete phase out of all unabated coal and oil power plants. And by 2050, more than 85% of buildings would need to be zero carbon ready, and almost 70% of electricity would come from either solar, PV, or wind. And at that time, you would also be taking about 8 gigatons of carbon dioxide removal out of the atmosphere. So this is big, big stuff. Let's not underestimate what is required. The other element that we've got there is that every pathway that limits global warming to 1.5 degrees involves some kind of carbon dioxide removal, and it serves 2 purposes. One, it can compensate for emissions from difficult sectors like aviation or heavy industry, but it also can help to draw down the amount of carbon dioxide in the atmosphere. And carbon dioxide removal techniques cover a wide range of different approaches, some of which we can do immediately, others of which need more research and development and investment to bring them forward. So not cutting down existing trees will help us, planting new trees, carbon capture and storage, which can be combined with bioenergy to get these negative emissions, and a lot of growing interest in so-called nature-based solutions involving the way we use land. So soil and livestock management, which can help to build up carbon stocks in agricultural land, restoring peatlands, which is a big opportunity in Scotland and Ireland, and various other land management approaches that can help you. But one of the challenges that has been identified by IPCC and others is the potential implication, especially of the bioenergy and anything that involves large-scale land use change, big implications for food and water security, and also for ecosystems and biodiversity, recalling that we have a biodiversity crisis as well as a climate crisis. I should also mention direct air capture of carbon dioxide, given a recent announcement about a pilot plant in Scotland that's going to try to extract carbon dioxide from the air rather than from power station gases. So turning to what it would all mean for the
1 minute, if that's okay.
Yeah, I'm just finishing the last slide. Yeah, so just for net zero in the UK, this is from the Committee on Climate Change's 6th Carbon Budget report, showing what kind of measures would be needed to take you from a kind of a business as usual scenario down to net zero. And I think there is obviously a lot on the demand side with efficiency and the changes in behavior, but the big orange slice is actually electrification. It's things like the move to electric vehicles, possible move to heat pumps in buildings. And there is another large blue chunk down at the bottom, which is low carbon energy, ever more renewables, but also a big chunk from using the way we use land and the way it's used for greenhouse gas removals. So that's the picture. It's not the only way of doing it, but it's the kind of portfolio that needs to be built up. And just to say, although I've described an IPCC report that's 3 years old, there will be another report on the physical science coming out in about a month's time, in time for COP26. And the other 2 working group reports will come out early in next year, early 2022. And I'll finish there, Stephen.
Brilliant. Thank you very much indeed for that. I think you can never remind us all too often that this is absolutely a global challenge, and that while we have a part to play perhaps in our own contributions and a leadership role, it's actually that it is a global challenge. So when you talk about the pledges that countries have made, and you said 2/3, I think 2/3 of emissions are covered by commitment towards net zero emissions. How big a gap do you think there is between the pledging and the policying within those 2/3 of countries who have committed to it? And is it too early to be concerned that we're not full throttle towards this, or do we really need to get on with it?
Yeah, that UNEP gap report really illustrates the size of the challenge. It's still about a quarter of projected emissions in 2030 is the size of the gap that's left globally. And some of the G7 pledges that come out will just help us. So I think the G7 countries are doing quite a good job. The big challenge remains about the other members of the G20 and what they may come up with, because they're a big part of the gap.
Brilliant. Okay. Thank you very much indeed. Right, we will move on to our next speaker, which is Dr. Jane Strachan, who is head of International Applied Science at the Met Office. And Jane, you're going to talk about building resilience and adapting to future changes. Jane, if we could have 10 minutes, please.
Hi, thanks, Stephen, and thanks, Jim, for your talk. So I'm going to take a bit of a sidestep onto a parallel pathway that we're going to need to follow alongside whichever mitigation pathway that we follow, because we've already locked ourselves into a degree of climate change that we will have to prepare and respond to. Stephen has said that I'm going to be talking about adaptation and resilience. When we talk about adaptation, we mean the ecological, the social, the economic actions, for example, that reduce the impact of the specific effects of climate now and into the future. In terms of resilience, this is more around the ability to limit the impact of a variety of effects. It's more about building a general capacity and capability to deal with multiple stresses, including climate change. So my team use the best available science and knowledge to help the UK and global society make more informed decisions in the face of weather and climate variability and change. And that includes using the information to help inform adaptation and resilience planning and policy. Now, when I say science and knowledge, it's important to understand that I don't just mean weather and climate science and knowledge. Climate science is very much part of that jigsaw to understanding how we can make adaptations to a changing climate, but we really need to understand that full risk picture, and that requires a multidisciplinary approach. The Met Office is a world leader in the climate hazard component, so that's the hydrometeorological physical events that we feel. But risk assessment requires an understanding of the exposure, so where we are geographically, for example, and what we're exposed to in terms of that hazard, and also vulnerability, so the socioeconomic situation and how that determines our ability to respond and to cope. So we have to work with strong local and international partners to bring in that expertise, and we work together and with information users to develop the climate risk information and tools that are fit for purpose. And this also provides the evidence base to make more informed decisions around adaptation and building resilience. So what I'm going to do, if I can share my slides, is showcase a couple of examples around how we are working in the climate adaptation and resilience area. I'm going to give a UK example and also an international example as part of our international development commitments. So just bear with me while I share my screen. Can you just let me know if you can see those slides?
We can see that.
Great. So the first example that I'm going to give is a UK-based example. This is part of the UK Climate Resilience Programme. This programme is built around three main objectives: characterising and quantifying the climate risks that I've been talking about, then managing those risks through adaptations, and working with partners to turn the climate information, the science that we produce, and the knowledge that we have available into accessible and usable climate services. So as we described before, these activities bring together climate science, but also experience from other disciplines and sectors. And this allows us to do multidisciplinary climate risk and adaptation research, while also building the UK's capacity for resilience to climate variability and change. So the next slide here gives you a snapshot of some of the work that we can do to take the climate hazard information down to climate risk information, working with climate sensitive sectors to understand what the impacts will be for them. So for example, it might be working with the energy sector to understand how cold weather and hot weather will impact the demand for heating or an energy, or the demand for cooling, for example, the change in ability to supply that energy. We might be working with the health sector to understand the increased risk of heat on sensitive sectors of society. It might be working with the agricultural sector to understand how the changes in the climate will affect crop growth and what adaptations the agricultural sector needs to take to be more resilient to those changes. Moving on to the next slide is a specific service that we've developed through this programme. This is the development of city packs. So these have been developed in response to the demand for usable synthesis materials for users in particular geographical locations. This pilot pack that I'm just showing here, a screenshot of here, I won't go into detail here, but this was developed for Bristol City Council. And feedback from the civil protection manager from Bristol City Council said that the information contained and also the process of co-developing the city packs meant that we've created a really useful local resource to inform a wide range of city stakeholders. This helps them understand how the climate is likely to change locally, and that really, really is important for the decision-making process, the impact that that could have, and why they need to take action now. And this series has been expanded to a number of other cities across the UK. Now moving on to an international example. So it looks like we're going global now, but actually this work also relies on us working with local stakeholders to develop capacity and knowledge. The example I'm showing here is the Asia Regional Resilience to a Changing Climate Programme, or ARC. This is work funded by FCDO through the UK Aid. And this work is working with partners in Nepal, Bangladesh, Pakistan and Afghanistan, with international institutions, including the World Bank and the World Meteorological Organization. This work aims to increase those countries, the region as a whole, resilience to weather and climate risks through enhanced regional coordination, building capacity, generating together tools for decision-driven weather and climate services. This project looks at a range of timescales, from weather all the way through to climate timescales. So for example, development and implementation of impact-based weather forecasting for severe weather early warning services. That might mean building local National Meteorological and Hydrological Centre capability to undertake that forecasting and deliver those warnings. Strengthening their seasonal forecasting activities and advice to vital sectors. So for example, working to deliver agricultural advisory warnings to farmers in Bangladesh. And improving the uptake and use of climate change projections to better guide, understand and communicate future climate risks to guide adaptation decisions. We also, throughout all this work, we try to co-produce the work that we're doing throughout the whole process. And in the context, we also include monitoring in terms of looking at the uptake of the information and the services that were produced, and also looking at the socioeconomic value of those information and services that are produced. And in the context of the ARC programme that I show here, we've been working with social scientists at the University of Leeds as part of the Met Office academic partnership. And this allows us to draw on expertise and learn from expertise in socioeconomic evaluations, an example of how we're drawing on expertise from around the UK and internationally. My final slide, I will try and bring us back to that, our aims for net zero. And how is the Met Office trying to align its activities to that aim? I'm going to specifically talk about our international work and how we're undertaking that. During the last 18 months, we've been able to continue to deliver our large portfolio of international commitments remotely. This has been made possible because of the groundwork that we put in place, for example, through established strong partnerships and relationships with international partners, which have built a strong base of trust, but also an expectation in terms of the way we work. Because we've already been involved in innovative international projects with partners, we already use a number of techniques that we were able to shift to remote ways of working, which has worked really well. And also our co-production of science and services with a stakeholder-led approach has really helped us still stay connected with the partners internationally. So we know that some face-to-face in-country activity will still be required alongside this remote delivery. However, our approach now will be to design the projects with funders, this is really important, and with partners to avoid business travel wherever necessary and explore low carbon alternatives. So we're aiming to build back better in terms of resilient development in general. We're also aiming to build back greener in terms of our mitigation aims. And with that, I'll stop and allow the next speaker to speak. Thank you all very much.
Jane, thank you very much. Very interesting. It struck me that obviously we have a need for climate scientists, but a lot of the adaptations to building resilience is going to require, particularly I was thinking of engineers with an interest in climate science. Do you think we are training the right level of workforce with the right skills to combine, hard-nosed engineering with understanding of climate change? And are you aware of any particular courses that are available and that are being run that we could point people towards? Because obviously this is an area of great interest to younger people, as they're likely to be the ones who are most impacted by the end of this coming century.
Yeah, that's a really interesting question, actually. And, this is the bread and butter of our climate services work, is that we know that we can't do this alone. We need to work with these other disciplines and learn together. Our team are a team of multidisciplinary scientists. Some have a climate background, some have engineering, agricultural backgrounds. So we're really trying to bring in that expertise and draw through our project partners on that expertise. Climate services is very much about drawing those disciplines together, and the Met Office and other organisations such as the WMO are doing a lot more work in that field. We're also developing climate services training, which is what you're suggesting here, bringing those disciplines together. How do we sit down and on a level playing field and work together to look at solutions to the problem that we're facing here?
Brilliant, thank you. And I'm sure there'll be further questions around some of the things we've talked about. Right, we will move on now to our final speaker, which is, where are we? Dr. Alex Archibald, Associate Professor and Group Leader for Atmospheric Chemistry Modelling Group in Yusuf Hamied Department of Chemistry, University of Cambridge, who is going to talk about climate mitigation, co-benefits and trade-offs. So, Alex, please may we have 10 minutes from you.
Thank you, Stephen, and thanks to all of the previous speakers, Jane, Jim, and Jason. I know I'm the odd one out today without a J in my name, but I'm just going to start sharing my screen with you and get my virtual laser pointer up, and hopefully you can see my laser pointer as if I was in an auditorium speaking to you in person, which hopefully we were not too far away from at this stage. So yeah, I'll talk to you for the next 9.5 minutes about choosing the right path, the co-benefits, and some open questions. I'm going to try and frame this around some open research questions of the net zero transition in the UK. And I'm really going to focus on physical climate aspects. I'm not going to touch on biodiversity. That might be something we want to discuss later. And there are certainly huge potentials for co-benefits in the biodiversity space. Largely, how I'm going to motivate this is based on a really nice review paper which was published last year by Neil Jennings and colleagues. So Neil Jennings and some of his colleagues work at Imperial College London, and they produced this report, a narrative review on mapping the co-benefits of climate change action and focus this around public concern in the UK. So this really provides some nice diagrams, and I'm going to just go through one of them here to outline some of the co-benefits of climate action, and we're just going to use net zero and climate action synonymously here. And we're going to talk about energy efficiency and how that can generate a huge range of co-benefits. So to begin with, though, let's kind of motivate why we talk about energy efficiency. And that's because at the moment in the UK, poor energy efficiency is having a direct effect on health of people that live in the UK. In the cold winter of 2016-2017, something like around 11,000 excess deaths can be attributed to poor energy efficiency in homes. And what I'm going to say is that I think net zero provides the framework and an opportunity for us to do something better and faster to tackle some of these problems, and this problem in particular. And why energy efficiency is really important is because if we can improve energy efficiency, we can look at this Venn diagram here of different components. So if we can think about the environment here in this dark green, health in yellow, housing in blue, and business and economy in light green. And what we can see is that energy efficiency is really the thing which sits at the center of this Venn diagram. So if we improve energy efficiency, we lead to a reduced energy demand, and so carbon reduction. So we're getting towards our net zero target. That then, for free almost, can lead to the reduced influence of cold-related illnesses, which has a knock-on effect for reducing NHS costs. If we think about what we've done to get to energy efficiency improvements, well, we've improved the quality of housing stocks. As a side benefit there, we've reduced the operating costs for housing providers, which may be local councils and local authorities. And then connected with that, well, to get the energy efficiency in the first place, we've had to grow an energy efficiency industry, which is creating green jobs, decreasing the number of days missed at work due to illness, because this is leading to a better environment for people to live in, and ultimately addressing one of the biggest problems we have in the workforce, which is around productivity and leading to improved productivity. And I think the abstract for this paper, I've highlighted the final bits in yellow, which I think really speak to some of the really nice aspects around co-benefits. And that's that city level and regional areas are particularly well placed to incorporate these co-benefits into their decision making, because it's at these regional levels that co-benefits most clearly manifest, and where interventions can have the most immediate effects. So I think there's some hugely positive messages around the pathway to net zero. I'm going to focus more on air quality because that's kind of an area of specialism of mine. But just to touch generally on the co-benefits of net zero to health and the NHS, well, one thing we've probably heard a lot about in the media is around diet change and the co-benefits of that. Just in terms of changing our diet to be something that's more in line with what the WHO think that we should be having, so reducing our salt intake, reducing our red meat intake, that will help reduce 7 million premature deaths in the next 30 years, and also go a long way to helping reduce carbon emissions from agriculture. The topic that, though, is closest to my heart is air quality. And if we think about the current situation in the UK, there's something like 40,000 excess deaths every year because of poor air quality. What's that cost? So that's something like £54 billion every year in costs. And we can just think about net zero again as being a lever that we have to mitigate this. And there are a multitude of different ways that we might do this and see this achieved. I think as we are moving away from the lockdown restrictions and working from home is being eased, we don't want to see the story on the left-hand side here, I'm sure. I'm sure what we'd all love to be able to do is actually use things like active transport to get around more. And that has benefits not only to the health, but also to the mind. But not every action comes without a cost, and understanding the trade-offs is really the key to this whole problem. And the late, great Martin Williams developed this cost-benefit analysis, or this trade-off diagram, to help articulate this. And so we have air quality benefits on the y-axis and climate benefits on the x-axis. And what we're trying to find are these win-wins where we have both a climate benefit and an air quality benefit. And Martin, back in 2012, articulated a number of these, including carbon capture and storage, low or zero emission vehicles as being in this win-win sector. However, we can just think back a few decades to think of examples where we've not done such a great job. So let's think of diesel. And diesel was really pushed because it is great for carbon dioxide. Diesel vehicles are very efficient. but it's terrible for air quality, and partly that high number of deaths that we have in the UK every year, 40,000, is associated with things like the large number of diesel vehicles that we have. What about biomass in homes? Lovely, it's zero carbon, so by definition, it's great in terms of our net zero agenda. For those of you that have a biomass burner in your home, a log fire, it creates a lovely ambience, but you're poisoning the local neighborhood. If we think about London just as a specific place, one of the major sources of air pollution at the moment in London really comes from wood burning stoves and their effects. So we really do have to kind of view it through this trade-off framework. And I think recent events, you know, like the lockdowns associated with COVID have helped us understand some of those trade-offs much better. So if we think about electric vehicles, well, electric vehicles won't solve all of the urban air quality problems that we have. And we've seen that because effectively during lockdown, we took vehicles off the roads and problems with particulate matter didn't go away. We have the same amount of particulate matter problems during the lockdowns as we had before them. Nitrogen dioxide really, really well managed through getting vehicle combustion engines off the roads, but particulate matter not. Reforestation, that will require, I think, some careful consideration about land management. Again, that kind of plays into the regional win-wins potentially. But just the increasing number of wildfires we're seeing means that there's a potential hazard there to think about managing. Even something as simple as hydrogen can lead to complex outcomes. And for the physicists out there, every physicist loves hydrogen because it's a very simple molecule. And what I want to show here in these pictures is what can happen to the global atmosphere under different scenarios of hydrogen economies. And we start in the top left with the current levels of hydrogen in the atmosphere, about 500 parts per billion, so tiny amounts. And this plot shows altitude versus latitude, so North Pole, South Pole, and the amounts of ozone in the atmosphere. And when it comes to ozone, you only need to know two things. It's good up high, but it's bad nearby. So in the stratosphere, it's saving our skin. It's a natural sunblock. In the troposphere down here at low altitudes, it's a toxic compound, kills about 1 million people every year prematurely and leads to billions of pounds of crop damage. And so what we can see, so if we go along here, if you follow my cursor, we're going to a quadrupling of hydrogen in the atmosphere under this scenario. These are just calculations. And what we see is an increase in the near surface levels of ozone. So that's making an existing problem worse, and a reduction of ozone in the upper atmosphere. We already have reduced ozone in the upper atmosphere because of the ozone hole. So again, this is exacerbating a problem of ozone. However, what we do with co-emissions, so these might be
Alex,
emissions of—
1 minute?
Yeah, I'm almost done. Yeah, this has things to do with NOx and CO and methane, really can flip the picture and can result in a picture which is really incredibly different. So even something as simple as hydrogen has really complex aspects to it. But to conclude, I think there are significant co-benefits possible for the UK under the net zero transition. And in choosing the right pathway, we'll need to think about the trade-offs, and there are regional opportunities. There is a need for some fundamental research, and I think computer models, as Jason has shown, really can play a key role here in identifying some of these win-win scenarios. So thank you, Stephen. Hopefully I've managed to stay under the time, and I'm happy to take any questions.
Excellent, thank you. Very, very interesting. When you displayed the I think it was the Williamson chart?
Williams, yeah.
Williams chart. Up in the win-win box, I recognised, you know, we're making good progress on some of those technologies, but the one I'm not sure that we're making here or around the world good progress on is tidal. Do you think that's a missed opportunity, and what are the levers we need to pull to make that part of the solution?
So I think, again, it kind of comes down to trade-offs. And so I grew up in Bristol. I was really interested to see Jane's infographics about Bristol. And there, for decades, we've been talking about tidal. And obviously the trade-off there is a biodiversity trade-off, and what's prevented, you know, some of the tidal work in the Severn Estuary is that the really you know, unique nature of that part of the world. And I think that's kind of true. There are many coastal zones which have huge biodiversity niches. So I think it's about trying to balance that and find the right places. One of the problems with, you know, renewable energy is sometimes you can create it where there isn't the demand. And so then we need to kind of think not only about generating it, but about storing it and moving it. And that's where hydrogen could play an important role.
Absolutely. Thank you very much indeed. And thank you to all our panelists for their contributions. Very, very interesting. We are now going to move to questions. And the first question is from our Vice President, Stephen Benn. Stephen.
Thank you all for the really interesting presentations, and I hope this isn't an unfair question. 2 weeks ago, Sir Patrick Vallance, Chief Scientific Advisor, told a parliamentary meeting called Links Day that he thought that we know already all the technologies that are going to make a difference to our efforts by 2050, and that we should just concentrate on making use of what we already know. Do you think that's a fair comment, or are there in fact technologies or approaches that you think we could still develop between now and 2050 to make a difference?
Thank you, Stephen. Jim, I think I saw your hand flick up.
Yeah, I'm happy to have a go at that one. I kind of partly agree with it, that we shouldn't just think that technologies are developed in the laboratory and then are suddenly available to be deployed. There's a number of stages that they need to go through. So the first thing is to say there's an awful lot we can be getting on with right now on the basis of established technologies. But there are other technologies where we understand the principles, but we haven't kind of demonstrated them and fixed the trick in engineering terms. And the carbon capture and storage technology would be one area in which you'd provide an example there. Other areas like renewable energy, say wind energy, for example, we've got pretty good at it with the very big offshore turbines that are going up. But you can go further with a little more development of the technologies. And then there are others that, frankly, the laboratory stage, it still counts. Things like developing electrolyzers to support the hydrogen economy, for example, if that comes through. So I think it's a mixed picture. We've absolutely got enough to be getting on with things, but we need to do R&D and some preparation for mid and later century as well.
Okay, thank you.
Thank you. Did anyone else want to comment on Stephen's question? Yes, Jason. You're muted, Jason.
It was bound to happen to one of us, wasn't it?
Yeah.
I just wanted to highlight one point, and you could see it in the scenarios that Jim showed and that I showed, and that's the technologies are not all on the supply side. Some of them are on the demand side and around efficiency. And it's not only technologies, it's also behavioral change. And I think it's really important to understand within the pathways that particular basket, and that different balances of that basket will be appropriate for different locations.
Okay.
Now I'm doing it.
The different behavioural changes around in different parts of the world, different nations.
Quite possibly, in that the appropriate behavioural change might be linked to cultural background, to history, and some might be more suitable for some locations than others. And I think this brings in the idea of thinking of a just transition.
Great. Thank you very much. Our next question, or it's a couple of questions, is from Heidi Bannister. Heidi, if you could pose your questions and remind us, if I could make this point to anyone who's asking a question, to not only state your name, but also the organisation that you are representing. Heidi, please go ahead.
Good evening, everyone. I'm just very curious to know, as a consumer, as well as being involved with the Society of Cosmetic Scientists, what we can all do as individuals. There's some great ideas here for the big picture and big plans, but as an individual on a daily basis, what should we all be focusing on? There's a lot of talk, there's a lot of media around specific things, but what should we as individuals be doing?
Who would, again, yep.
Yeah, I'm happy to pick this one up. And just one thing to flag, I mean, a lot of the scientific work that's more on the social science and the economics side is showing that it's not just people changing their behavior in terms of having a shorter shower or turning the light off that makes a big difference. It's about the way that people interact with technology that is a clue to a lot of the bigger changes where behavior might get you. So choosing your next car in the right kind of way. When you have to get to a boiler, think about the heat pump or the other ways of doing it. These are the things that will make the bigger kind of difference. But just to flag, if it was pure behavior, the absolute answer is fly less and eat less meat. These would be the two things that would make the biggest difference. But just to say, as someone who steered the IPCC special report on climate change and land, the last thing we scientists want to do is tell people what to eat. We use the word choice and behind the word diet every time we use the word diet, because we can point out the implications to people, but this is a very culturally sensitive area that we need to look out for.
Thank you. Anyone else want to comment on what individuals can do?
Just to note that we can also make ourselves more resilient. So just as we're seeing impacts in the present day, we can individually look to see how we can be resilient to flooding or high temperatures, for instance.
Great, thank you.
Just muted yourself, Stephen, there.
Sorry, thank you for that. The next question is from Dima Kunda. Dima.
Hello, can you hear me?
We can.
Yes, I believe I had a couple of questions, but the first one I remember is in Professor Jason's lecture, when you were showing us the models as they're extrapolated up to 2100. And I'd like to know more about the assumptions made that differentiate each model, because we're making very big assumptions when we're doing modeling over such long period of time. And the next comment I wanted to make was about biofuel and how we're constantly referring to it as a net zero emissions energy source. And as a chemical engineer, I know that in many cases, biofuel, it's very hard to define it as a net zero emission energy source, because you're still having to put heating duty, cooling duty into these reactors. We're assuming it's net zero because we're assuming the bacteria, as it's consuming CO2 as it's producing our methane in biogas. But it's not it's in many reactors and chemical plants, it's not an exactly balanced equation. So that's just a comment to make about biofuels. Yeah.
Thank you, Dima.
Shall I take the first part of the question?
Yes, please, Jason.
So we could spend hours talking about the assumptions. What I would say as a starting point is the models that we've used of the climate system, they're based on our physical understanding. They're not, for instance, simply statistical extrapolations. They are based on physics that in many cases has been around for more than 100 years. Also, we compare those models with the real world in the present day, and also the change over past decades. And it does show us that those models have skill in many aspects of reproducing the real climate, but they are uncertain. So for instance, there's a big debate over what scale or resolution the models need to use. And what we tend to do is run a whole series of models with slightly different assumptions and look at that range of outcomes when thinking about which pathways might be more appropriate or which adaptations might be more appropriate. The IPCC reports that Jim mentioned have very good sections in the Working Group 1 report over the model assumptions, and I'm happy to pick it up further offline.
Thank you very much. Just on the point of resolution, what resolution do you normally operate to at the moment?
So for the global models, most of the simulations are around 60 kilometers. So we've split the world into 60 kilometer boxes. We've got some experimental simulations that go down to 12 kilometers. And actually, we're seeing some really exciting things in those, such as where we place the ocean currents that we may need to take into account. When we look locally over the UK, then we're starting to use the resolutions that have been used in weather forecasts. So the UK climate projections go down to about 2 kilometer scale in terms of the resolution. And that means you can actually represent atmospheric convection rather than representing it by a simple approximation.
Excellent. I mean, presumably if you, on the global scale, if it's 25 times higher resolution, that means 25 times the computing power to be able to process those models, doesn't it? No, good, correct.
It's worse. It's worse than that because you've got it in both directions, and you might want to have more in the vertical as well.
Okay.
So it becomes very expensive.
Yeah. Fantastic. We'll lobby for a new supercomputer. Right. The next question is from, well, it's an anonymous attendee, which I can't actually see in the participants list, so I don't know who that was. And so therefore, as soon as I can't see them, I'll move on to the next one, which is John Lowe. John, good evening.
Unmuted, good evening. Jason, how strange to find a J. Lowe facing you this evening. But a difficult question to answer, and I don't expect you to have a solution, but what about population reduction globally?
Jim.
Yeah, happy to come in on that. I mean, the IPCC reports have really set out quite clearly what the relative contributions to rising emissions have been. And the answer is that about a quarter of it, roughly, is driven by population and 3/4 by rising incomes and increasing wealth and consumption of every individual. So population is part of the picture, but it's far from being the most important driver of change. And many of the studies that are being carried now, they're starting to look at, for example, what would be the implications of increasing or decreasing population growth in lower income countries, which already have quite a low carbon footprint. And the impact is surprisingly low, actually. The bigger problem or the bigger issue to be addressed is consumption and production patterns rather than the population side. It's not completely unimportant, but it's not the biggest factor.
That's a very interesting viewpoint. Thank you for that. I shall remember that. Thank you.
Excellent. Thank you very much. Our next question is from Dr. Lisa Baldini. Lisa.
Thank you very much. I was just wondering if the panel had an opinion on exchanging landfills that are known to produce methane with waste to energy incinerators that produce nitrous oxide, another greenhouse gas, and also have potential other airborne toxins. Is this something that, you know, is a viable alternative or not?
Who would like to, again, Jim, please?
Yeah, again, a lot of them are going towards the mitigation side. So yeah, I mean, look, landfills and waste, you know, are part of the picture, and it's a significant part of the UK's inventory, but it's far from being the biggest part of it. And my guess would be, if you have good pollution control equipment on an incinerator, the impacts on climate change are going to be positive rather than going to landfill. And there are all sorts of other reasons why we might want to landfill and pay more attention to recycling is probably the most important part before you go to incineration. Landfill, I think, would be at the bottom of the waste management ladder.
Thank
Could
you.
Could I jump in as well? So maybe just as on a global context as well. So methane is very high on the agenda towards net zero, and Jim showed that slightly in some of his slides. And I think one of the most important things we should be encouraging as a global society is preventing food waste going to landfill, particularly in tropical regions where it leads to large levels of methane production. And different, places I've lived in the UK seem to have very different approaches to household sort of organic matter recycling. And I think there's some great examples there of great work that's done, and other places probably need to catch up slightly.
Thank you very much. I think the next question is also for you, Alex, which is from Matthew Cotton. Matthew?
I'm not sure that he's in the attendees list, actually, Stephen.
Oh, sorry.
He seems to have gone, I think.
Oh, okay. I'm sorry, I didn't check that on this occasion. Okay, well, sadly, he's not going to be able to ask his question. In which case, we'll go to Paul Jackson. Paul, good evening. Paul, you're muted in case you are speaking.
Okay, I should be unmuted now.
You are indeed.
Wonderful, wonderful. So I asked this in the context as a council member of the committee, but also I am a pro-chancellor at the University of Essex and wrote a report on skills for NCUB last year. So it's engineering skills that I'm particularly interested in. And Stephen touched on this already. And I wonder if you could tell us a little bit more about your perspectives on the skills that are needed to support the move to net zero. I mean, is it good enough that we still teach about internal combustion engines on mechanical engineering courses? I mean, can they do a master's that then gets our students into really productive people heading towards net zero? Or do we need a major overhaul of degree content, working with the universities and presumably the professional bodies that accredit their degrees?
I don't know, Jane, if you wanted to say anything following your earlier comments, and then I'll go to Jim.
Yeah, I'd probably kind of take that broader, actually, and it's not just about kind of university skills and engineering skills, but actually skills across all industry that need to rethink how they're doing things. So like the fashion industry, fashion is a huge contributor to the climate problem, the food industry, even things like retraining car mechanics who are, they're going to have to switch their whole way of working to electric vehicles. So it's not, I think that we do have to have an overhaul, but I think it's across all sectors of society, all areas of industry.
Thank you. Jim? Oh, and then...
And just to agree with what Jane said, I've just finished chairing the Scottish Just Transition Commission, which addressed a lot of these skills type of issues. And it's really across the board that we need to make the changes. So we identified big opportunities, more apprenticeship kind of level, for example, in the housing retrofit opportunities that have been set up. There are actually opportunities in terms of land use, maybe not quite the high skilled jobs, but the peatland restoration, tree planting are all big creators of employment. And not to forget that general sort of trends like digitalization are important and can be applied in the energy sector as well. So applying these kind of skills to things like managing much more complex electricity networks is something that we should do more of. But just to also emphasize with Jane, it's not just a case of sort of early years training. I think continued retraining throughout people's careers is going to be really important as well.
Thank you. Alex, I think you wanted to add a comment.
I completely agree with Jane, and in particular Jim's last comment about the lifeline of training. But I would also just say I think fundamental topics still provide a great grounding and a great a great way for people to actually make impacts and inroads into some of these areas where it does require some potential insight into unrelated topics, is where some breakthroughs can come through. So I'd also make a plug for the fundamental and classical degrees as well: physics, maths, chemistry.
Brilliant. Thank you. Right, our next question is from Paul Ridout. Paul. Hi there.
Hello.
That's it, we can hear you.
Yep, that's Paul Ridout. I'm a marine scientist and vice president of this committee. My question to the speakers really is that the UK government COVID programme has been driven significantly by science and scientists. So do the speakers believe that this is happening sufficiently for climate change mitigation? When I say this is happening, are the scientists, is the science and are the scientists being listened to and acted upon?
Thanks for that, Paul. And I'd like each of your views on that. So perhaps start with you, Jim, and then I'll go across my screen.
Well, how can I try a very brief answer and say that we're being listened to but not necessarily acted on at the moment? I think the challenges are very large, and any policy decision is a mixture of values and scientific input. The science will not be the absolute determinant. It's got to be mixed in with political priorities as well. So with all the net zero kind of targets, I think we're being listened to. It's the next stage, whether you act on it and put the measures in place.
Great, thank you for that, Jim. Jane?
Yeah, so for this one, yeah, I think I think what we really need to be doing is making climate smart decisions in general. So, and that means that we're not looking at climate as the kind of initial starting point of the solution. This is part of the bigger solution of how we develop in the UK and internationally. And that's mitigation is part of that, and adaptation is part of that. And I think that's starting to happen, but slowly. So whether, I think we need to do a lot of work in terms of scientific communication and turning that information that's coming out of the models, for example, into something which is relevant and usable, and people can see how it's going to impact their decisions in businesses. That's where our work is in terms of adaptation and resilience building. So it's kind of that climate smart decision making and taking that information down to something that really matters to people.
Thank you. Alex, and then Jason.
Yeah, personally, I don't have much more to add. I mean, I think we're in a good position in the UK with things like the CCC, and that provides this independent scientific input. But from the input to decisions, clearly there's some complex drivers and levers involved. Over to Jason.
Jason.
Yeah. So, I mean, on one sense, we just have to look, and then we see something like the Paris Agreement and the number of people signed up to that. So clearly the scientific message is getting through that really allowing warming to reach the higher levels is associated with very strong impacts. But the scale of really being able to limit that warming, that's indicated by the NDCs. And I think we saw in Jim's talk in the gap report that there is still a gap, and the science is highlighting that gap on the mitigation side. And it's because of just how big and unprecedented the changes are globally. In the UK, of course, we do have carbon budgets that take us out quite a long way towards the net zero transition, and I think that is an achievement to see the science interact with policy in a way that actually takes that into law. I think on the adaptation side, we also see advances. So, of course, we've just seen the most recent climate change risk assessment take a step forward. We're going into the national adaptation planning phase, and we see individual examples of where the science has informed development, such as, for instance, around reviewing the suitability of the Thames barrier. So as a Met Office scientist, I certainly see routes where our information is really feeding through to inform decisions. The public side of things, I think, is encouraging, because if we look at some of the recent surveys in the UK, going back 5 years, people were concerned about flooding, but not so much high temperatures. Recent work shows that concern now is extended further, but there's still some way to go in terms of taking the positive message about what individuals might actually do about it in terms of acting.
Excellent, thank you. And I think we have possibly time for one more question. Depends on how quickly, well, or maybe even two, but let's certainly go for one, which is William Duncan. William, are you there? I know that Alex has sort of given you an answer in the chat, but it would be interesting to hear the exchange for all of us.
Thank you very much, Stephen. Yes, I hope a simple question, but I was slightly puzzled to hear that the particulate levels had not gone down so much during the lockdown period. And I wonder if there could be an explanation to that and whether it was expected. But finally, can I just congratulate all the speakers on absolutely fantastic presentations, so illuminating. Thank you.
Thank you, William. So, Alex, do you want to kick us off? Yes.
Yeah, and thank you, William, for the kind comments. And I agree, really fantastic talks from everybody. So during the lockdowns, what we really experienced was a cessation of private vehicle transport, largely. That's kind of the biggest thing that happened. People stopped driving around in private vehicles. And private vehicles are generally combustion engines, which produce gaseous pollutants such as nitrogen oxides, in particular nitrogen dioxide is kind of the really bad one. Particulate matter tends to come from a smorgasbord of different sources. So your wood fires, as I said, in London, one of the biggest sources of particulate matter. But across the country, it's things like agriculture, sea spray, building work. These all produce and contribute significantly to the total amount of particulate matter. And actually, the combustion engines related with vehicles and private vehicles in particular have a small role to play in making those particulates. So we could see from space, NO2 levels dropped dramatically, but actually it was probably anticipated that particulate matter wasn't going to drop. And yeah, across the UK, particulate matter really didn't change during the lockdowns. And then it will be behavioural change and other mitigations in the future as we go to net zero that might affect that.
Thank you. I don't know if anyone's got a final comment they want to add on anything. No, in which case, as it is 1 minute to 7 and we are due to finish at 7 o'clock, I just want to say a huge thank you to all four of our speakers, to Jane, to Jim, to Jason, and to Alex. I think it has been a really informative and stimulating evening. Of course, I'd like to also thank Kirsty McBeath and her colleagues at the Met Office for helping us put this together. And of course, my usual thanks to the Parliamentary and Scientific Committee team of Lee Jeffs, Karen Smith, John Slater and Alfie Hoare, who will be writing a report up of this evening's discussion that will be published in our quarterly magazine that's delivered to all members of the House of Commons and Lords, Science in Parliament. And so it'll be seen by a much wider audience than those who were lucky enough to be here this evening. Our next meeting will be on Tuesday the 13th of September at 5:30, when we will be discussing mathematical modelling and algorithms, which we are holding in partnership with the Institute of Mathematics and its applications. Thank you all again to my contributors, to the panelists, to the team, and of course to you for attending and for your questions. And I very much hope you have enjoyed it as much as I have. And I look forward to seeing you again at the next Parliamentary and Scientific Committee discussion meeting. But until then, have a great summer and good night.